now going to talk to you about random signals and additive white Gaussian noise. I'm particularly interested in the concepts as they relate to the digital communications course. There is no prerequisite for you to have followed a random processes class before taking this course. So mostly this is background to make you have an appreciation for some of the concepts that are the basis for digital communications in terms of the randomness of the signals and the randomness of the noise. So consider this background, but not necessarily something that you would need to know for an exam or for any sort of evaluation. So we'll start with the mentioning that this is covered in section 1.5 of the Scholar textbook. And I'll be talking today about the power spectral density, about random processes, and about additive white Gaussian noise. And in particular, when I talk about random signals, I'll try to give you an appreciation for what the difference is between a random variable and a random process. And within the selection of random processes, we'll be considering those which can be classified as stationary or ergodic. And I'll give you some definitions of what those mean and why we would restrict our attention to this type of signals. And I'll give you some particular examples to illustrate some of the definitions. And finally, I will do a specific calculation of a power spectral density. So we'll take you through this, which would be, let me say, a standard exercise in a random processes class. And again, my objective is just to give you a little bit background on this. And of course, we'll end with a discussion about additive white Gaussian noise, one of the most important random processes we'll be working with. And because it's Gaussian, it has some very simplifying characteristics, which makes it extremely easy to work with. And so I'll be pointing those out today as well. So random variables, one of the prerequisites for this course is indeed a probability theory class. So you certainly all know what a random variable is. The distribution function, which we typically write as capital F of x, and the probability density function, which is typically the lowercase f, x of x. And the capital X in the subscript here refers to the random variable, so capital letters would be random variables, and the small x here is a realization or sample from the random variable. And an important function that we operation that we perform on random variables is the mathematical expectation or the mean of a random variable. We use the notation E of x, and we find E of x by taking the integral from minus infinity to infinity of x times the density function. So we weight the density function with the random variable realization value x, and this gives its mean value. So this is a random variables concept that you should be very familiar with, very at ease with. And now we move on to what is a random process as opposed to a random variable. I like to think of random variables as something being sort of something you pick out of a hat. So I have a hat, I have a bunch of balls in them, they can be red or black balls, and I reach in and I pull one out. And that is sort of a sampling, and there's a probability distribution for the balls in the hat. There's 5 balls, 3 are red, 2 are black, or something like this. But it could be also the idea of a unit number which is uniform between 0 and 1. I reach in the hat, I pick out 0.0776. So it doesn't have to be discrete, it could be a continuous random variable. But there's this idea of picking randomly, and that it would be taking a sample from the distribution. Now when I do this to a random process, when I reach into that hat, what I pull out is not one number, not one random variable. What I pull out is a function of time. So here I have the capital X, which represents the random process, but this is a function of time. And now I've reached in the hat, I pull it out, and that's one realization of the random variable. So that would be x1 of t. If I reached in my hat numbers time, each time I pulled out, I would pull out a different temporal function. And this is what a random process is. It is a sort random process is one that has a time dependence on it. So I can think of the underlying sampling space for this random process, and reaching into the hat means taking one sample, and what comes out of the hat, as I said, is one of these functions in time. So if you were going to use some formal notation, a way to write it would be that the ith sample would be a function of time, and this would be the random process sampled at time, as the picked out the sample S of I. So what is the way of visualizing the difference between a random variable and a random process? Well, the random process is the function of time, but now imagine that I pick a certain time, time tk. Well, then I can think of each one of the samples at time tk. So I pull it out of the hat the first time and I look at what was the value I got at precisely at time k. And if I did that for all of the samples I realized, that would be like drawing from a random variable. So it would be like now I'm focusing on what was that one value. So now if I look at this sampling, if you like, of the time sample of this random process, now I get a random variable. So at a particular time, a random process becomes a random variable. Now, this is a function of time, which means I have many random variables that can be derivative from the random process. I can pick time tk, and I can pick some arbitrary other time tj, or anything, right? So there's a continuum, an infinite number of time samples, instance that I could be looking at. And that really is what makes random variables so much more difficult to work with, which makes random processes so much more difficult to work with random variables. So to give you a feeling for that, let's remember your random variable class. And let's pretend we're looking at just two random variables. And one way that I could visualize the behavior of two random variables would be to do something called a scatter plot. And a scatter plot lets us visualize the relative frequency of this ordered pair of two random variables. So I reach in the hat and I pull out an ordered pair, an x and a y. And suppose I plotted the x and y's that I got from these different hats I can pull from. And each hat represents a different fundamental sampling space, a certain probability density function for these random variables x and y in this example. And here are four different scatter plots which came from four different hats, came from four different systems with four different kinds of randomness to define these variables x and y. And for instance, we can look at the plot here on the left, and everything seems to be very uniform. Seems to not matter whether it's x or y. And then we look at the extreme here on the side, and we can see that some combinations of x and y are extremely unlikely, and others are highly likely. Happen a lot. Relative frequency is high. So you can see that these are very different behaviors that we might observe in a pair of two random variables. And if we want to quantify or describe mathematically the stochastic behavior of these two random variables, how would we do that? Scatter plot is a way of visualizing, but how would I quantify with the variables that are underlying this? Well, to do that, I would use what we call a joint probability density function. This would be a two-dimensional function that shows me the density of these considered as a function of two variables. And so, for instance, for this last system, it might well be described by really something that is a joint Gaussian function, for instance, like this. And what we're familiar with is if I took a projection of any one of these for x, for instance, or y alone, that would give me the marginal probability density function. So this is a probability density function of x and y together. And if I were to average over one of these variables, I would get the marginal, which would be the probability density function of a single random variable. So one PDF, that's simple for one random variable. If I get to two random variables, I'm going to have a two-dimensional. And so what happens when I start talking about this random process? Well, if I want to completely describe the stochastic nature of a random process, I would have to know the joint density function for any two, for instance, for any three, for any four random variables which are derivative from these random processes. And you can see that That's a great deal of information I require in order to have a complete description of the stochastic behavior of a random process. This is why random processes, much richer area, but also a much more complex mathematical framework to work with. And often this information is simply not available about some random processes. It is very difficult to know. So it might be easy to know what is the PDF of this random variable at a given time. And so I might know the PDF at this value of time. Now, it's entirely possible that at another instant of time, the probability density function could be completely different. So this is one complexity of random process versus a random variable. However, it's, like I said, it's much worse than that because the marginal distributions might be different, but the joint densities between them could also be very different depending on when I am doing my time reference mark. So very complex to deal with random processes. So probability density functions are the way to think about these random processes. It's random, but it's a function of time, which means that there's all kinds of correlations that could be happening. So our joint density function in the case of the two random variables that I gave showed the correlations between those two. But now when I'm talking about random processes, there's all kinds of correlations that could happen. So I need to have this sort of joint PDF between any sort of time points in the process, and perhaps extremely expects. So what are we going to do? How do we deal with this? And one way that we can deal with this is to restrict ourselves not to the family of all random processes, but let's look at some random processes which are tractable, for which we can do some manipulation and draw some conclusions or look for some intuition. And so we'll be considering now reducing the set of random processes to focus our attention on ones where we consider two moments. So a PDF probability density function, a joint probability density function, has all of the correlations and behaviors there. A moment is like an expectation, the mean. The first moment would be the mean. The second moment might be the expected value of the square. And so we're going to be looking at the expected value of the mean, and we're going to be looking at the autocorrelation function. So if you remember when we talked about power spectral density, we started that discussion with looking at an autocorrelation function, realizing the autocorrelation function had this relationship of the Fourier transform pair with the autocorrelation. And so now it's not surprising that we're looking at the autocorrelation when we look at random processes in order to create a tractable set that we could be interested in. So let's move on. And the one that we're going to simplify to is not only to just look at two moments, only think about the mean and the autocorrelation, the expected value of the autocorrelation function, but we're going to consider processes which are what we call wide sense stationary, WSS. So now I'm going to be discussing with you what is this subset, all the random processes, only not consider the PDFs of all the random processes, only consider two moments of the random processes. And then we're going to look at within that certain processes where these two moments have a certain kind of behavior. And that's called wide sense stationarity. So here we have these random processes, and I can imagine taking different time references and calculating what is the expected value at these different time references. So I have a PDF for the T1, PDF for time T2, etc. And suppose I now form the expected value at each one of these time instants, and of course that would also be a function of time. So what is the mean value at this instant of time? So I would look at the PDF at this instant of time. I'd find the expected value for that PDF, and that would be the mean here, and then I do it again and again and again. And so in this way, I would come up with the expectation function of this random process, the first moment. So here is one process. That was the first moment. How do I get the autocorrelation function? How do I get the second moment? And the way I'm going to do that is I'm going to think about this random process that I have, and I'm going to think about a time lag between 2 points in this random process. So here I picked, like in this illustration, 3 different points, but I'm just going to start thinking about lags between these points. For instance, suppose I take 2 different ones, T1 and T2. There's some lag between them. That's what I'm going to call tau. But if I define the autocorrelation function for a random process, well, it's going to look a bit like what we did before. There would be this product at 2 different times, T1 and T2. And then I would normally take an integral of the lag between them. But now what I'm going to do, it's a little different with random processes, is I'm going to take the expectation of this product of the random process with itself at a certain time reference. And of course, the expected value of these product of 2 random variables, because I'm looking at a certain instant of time, so each one of these is a random variable. And the way I find it is that I do a double integral, averaging over each one of these 2 random processes in the product. And of course, I need their joint density function in order to find this expectation. So I assume that I know the joint density function at 2 arbitrary points in time, and I integrate over them to get the autocorrelation function. So this is the definition of the autocorrelation function in the context of a random process. So at time T1 and T2, well, I define 2 random variables which occur at this time 1 and time 2. And then once I'm dealing with random variables, I know that I can take the expectation operation on them. And the expectation operation requires that I know the joint density. And so that is this density we see here. And I average this product over that joint density function. So the autocorrelation function is well defined for a random process. So this is the second moment. So instead of doing all the possible analysis, instead of requiring the entire PDF for every possible sampling and combination, I'm only interested in this particular function. Now, suppose I look at the behavior of this, and I consider now a certain lag between them. So now I'm going to think about tau. So now I'm going to think about xt1. And now what happens with how related is the same process if I look at a lag of tau? So here I am at T1, and I'm wondering how is the behavior between this random variable and the random variable which is located tau at a distance of tau. And I could have started at xt2 and wondered how is the behavior with a lag of tau from that one or from some other reference point. So what I'm saying is that I could sample at any time, but I'm wondering how much interdependence is there between this point and one which is tau away, no matter where it may occur inside of the time. Now, if I want to deal with wide sense stationary, now I'm trying to get to the definition of what this term is, it's kind of dealing with these 2 moments. The first moment being the mean, and the second moment being the expected value of the product, so therefore the autocorrelation function. So wide sense stationary, it's going to be this lag, which is going to be a deciding characteristic. So let's go to this. What is wide sense stationarity? Well, the first thing is a random process which is wide sense stationary is one where the average is actually constant in time. So although I calculate the expectation for each instant of time, if when I do that calculation, the result never changes, I always get the same value, then we would say that the mean value is constant in time. And that's one of the requirements for having a wide sense stationary process. So that this function in time, in the end, is not a function in time, but is a constant. The second behavior that I'm looking for to call a process a wide sense stationary process is that this autocorrelation function, when I pick any 2 instants of time, doesn't matter where those 2 instants of time occur from -infinity to infinity. What matters is how far apart they are. What is the lag between them? So what matters, how correlated the signal is whether they're 5 minutes apart or 10 minutes apart or 20 minutes apart. And it doesn't matter if I make this assessment on a Monday or a Tuesday or a Friday. So, you know, the big position in the time scale doesn't matter. What matters is the relative position. So when the autocorrelation function is a function only of the time lag and not the absolute position in time, in that case, we're going to be talking about a wide sense stationary random process. So these two criteria. First criteria, that its mean is constant in time. Second criteria, that the autocorrelation function is a function only of the time lag and not the absolute time position. So now I can go back a little bit to my discussion that I started previously, which was about power spectral density. I said that the power spectral density is relevant for random processes. And the random processes, or random signals, are defined as having a power spectral density only if it is a wide sense stationary stochastic signal. Okay, so the concept of a power spectral density is not applicable to all random processes. It is only applicable to those random processes which are wide sense stationary. Because when they are wide sense stationary, then the autocorrelation function is only a function of the lag. And therefore, we start looking at the idea of a Fourier transform pair. So wide sense stationary allows us to define the autocorrelation function as simply a function of the lag, and therefore it falls into the category that we've already discussed at some length, that this function is by definition symmetric, achieves its maximum at a lag equal to 0, and there's a transform pair which defines what is the power spectral density. So for a random process, which is wide sense stationary, the power spectral density is found via this autocorrelation function. In particular, for a wide sense stationary process, it is a strictly positive quantity. The power spectral density is always positive, the symmetry. So this is really what we discussed earlier, nothing too surprising, just another notation when we're doing with random variables. So now let me give you a couple concrete examples just to make things a little bit clear about how would you go about showing, demonstrating that a random process is indeed wide sense stationary or not wide sense stationary. How do we test it? Well, we go back to the definition. And let's take a simple example, which is a cosine function with a random phase. So here is, my function here at the top. I have a certain fixed amplitude, a cosine at a certain fixed frequency, but there is a phase offset, and this phase offset, that's a random variable. Now, every time I reach into the hat, I come up with a single phase, but that gives me a different function of time. So here's my function of time. Every time I reach in, different function of time. Now, it's quite easy in this case to calculate the expected value of that random process at any instant of time, because the density is very simple in this construction. And so I start, is this a wide sense stationary process? Well, this mean should not vary with time. And now I'm going to calculate, does it vary with time or not? So I'm looking for the expected value of this random process. So I take this random process, x, that's going to be a cosine. So I'm looking for the expected value of a cosine 2 pi FCT plus theta. And so I take this and I average it over the density for this random phase. And in this case, I'm going to assume a density of uniform probability for the phase over 2 pi. So theta doesn't vary from minus infinity to infinity. Theta only varies between 0 and 2 pi. And the density itself is 1 over 2 pi. It's uniform for all of it. So this integral is easy to calculate, and it takes the cosine, averages over one period, and that gives me an average of 0. Cosine has 0 average over 1 period. So the mean is constant with time. No matter what time instant it is, it's going to give me a mean of 0. Now let's look at the autocorrelation function, which is a function, now I assume, 2 different periods of time, t1 and t2. And I'm going to calculate what is the expected value of this product. So that's easy. It's the minus infinity to infinity. I take the product and again average it across the probability density for this random variable, which is the phase. So I replace that density with 1 over 2 pi, replace the integration from minus infinity to infinity, it becomes 0 to 2 pi. And I can use, this is the product of cosine, so I can use a trigonometric relationship in order to change this into a sum of cosines. And so this product becomes the cosine of the difference between the arguments of the cosine and plus another cosine term where the argument is the sum of these in the product. And so when I do the sum, well, when I do the difference, the theta here and the theta here cancels out, and I have a difference in time. And when I get the second term here, it's the sum of these two, and now I get a 2 pi. So now there's 2 terms in this integration. One of the terms has no pi in it, no theta in it, and one of the terms has a theta inside of the cosine. So the first term has no theta in it, and so the integral is simply multiplying by 2 pi. And in the other one, there is a theta, and that means that when I average over this cosine over an interval of 2 pi, it's going to give me 0. So this term goes to 0, and this one becomes a constant times the cosine. So the autocorrelation function in this case is a squared over 2, and it's cosine of 2 pi fc, and we can see that the t1 and the t2, it only occurs in this equation in the form of the difference between t1 and t2. So it's only a function of the lag and not a function of the absolute position. So we can replace t1 and t2 by tau, which is the difference between t1 and t2. And so this Rx of t1 and t2 is just Rx of tau, the difference between the two. So now I have completed my demonstration that this is indeed a wide sense stationary process, because first of all I showed that the mean is constant and always 0. Secondly, I found that the autocorrelation function is a function only of the lag in the time. So this is a wide sense stationary process. Now let's show you a counterexample, and it's funny, but the counterexample is pretty much the same one, except in this case I'm going to assume that what is random in my signal is the amplitude, and the phase is fixed. So the phase is fixed, but the amplitude itself can be random. And I'm not even going to say what the density is of that amplitude A, just that it's random. Because I'm going to take the expected value, and now I'm going to say the expected value of A times the cosine function. And of course, the cosine function, there's nothing random here. The only part that's random is A, so it becomes the expected value of A times the cosine, and so I have mean of A times the cosine here. And this is not constant in time. You may say, well, it could be constant if the mean was 0, and that is certainly true, but in general, it would not be. But let's go on and look at the second condition, which is the autocorrelation function. And in this case, the autocorrelation function is going to be Rx T1, T2, the expected value of the square of A, multiplied by this product cosine T1 and T2. And this is certainly not a function only of the difference. And because of that, certainly we might have had a process where the mean of A was 0, but you couldn't have a process where the variance, the expected value of A squared was 0. That would not be an interesting process. So this would be a counterexample. It's certainly not wide sense stationary. So having defined wide sense stationary, having seen some examples how to demonstrate that a process is wide sense stationary, it's not wide sense stationary, I'd like to just introduce a second idea, which is ergodicity. And ergodicity is something it's more practical in terms of being able to demonstrate this in the laboratory. So in order to find the mean, the expected value, then I had to have knowledge of what is the underlying density function. For instance, for theta, I needed to know what was the distribution of the random phase. Often this information is not available to us, but one thing that we can do is to see the behavior as a function of time. So it would be nice to be able to average over time and know that averaging over time was going to give us the same answer as averaging over the probability density function. And if indeed these two kinds of averaging give the same result, then we say that the system is ergodic. And so we're contrasting time averages with stochastic averages or expectations, which would be what we would use in a wide sense stationary analysis. So let's just see if I can illustrate for you what we're talking about now. If I look at each one of these is a different sample of our random process. And when I talk about the function at the mean of this function for a short interval of time, and then a longer interval of time, and a longer interval of time, until I've been able to observe this function for all time, then I could talk about the average, which would be UX. So there's two different things. One is talking about stochastic mean, where I have the probability density function, and I do the stochastic mean, and if it's a wide sense stationary process, it gives me one constant value. And the other idea is to take the time average. So no matter when I sample this, if I do a time average, and ideally over infinite time, but in the limit there's some average, and if all of these averages, the average in time gives me a mu-x, and the average stochastically gives me a mu-x, and these two things are equal, then I say that this random process is ergodic in the mean. So ergodicity is a concept where the time averages give the same results as the distribution averages, or the time average is equal to the ensemble average. So if a function really, if a random process is stationary, then certainly it will be ergodic. Of course, something is ergodic doesn't mean it's stationary, but ergodicity, at least it's something I can measure in the lab. I can actually find time averages for the whole signal, or for certain lags, what is the time average. So ergodicity is something that we might use as an appeal to our system. It's probably, there are reasons why we believe it's ergodic, and therefore I'm going to take time averages, and I'm going to assume that this is equal to the averages in the stochastic sense. And in the book, you'll see a list of what they call equivalences, what you would measure in the lab, and what that would tell you about the stochastic means. For instance, the DC level of the signal would be the same as telling you what is the mean of this random process. And I'll let you do the reading to find out some other equivalences. Another example that we can give is on the autocorrelation function calculation for a random series of bits. So I think it's instructive to look at this because that will let us get to a power spectral density, which we didn't really do in the previous example. So in this example, finding the autocorrelation function, and then we're going to go on to power spectral density. And in this case, we're going to assume we have perfectly rectangular pulses. And these perfectly rectangular pulses are modulated by a random binary sequence. So I have a DC level which is 0 because they're random variables +1, -1, and the plus and the minus occurs with equal probability. And I'm going to assume furthermore that the data is independent, which means that there's some bit here, next bit here, and whether it's a 1 or -1, completely independent from one time interval to the next. So what I wanted to find is the autocorrelation function, and to find that, remember, I'm going to look at this sequence, this random sequence, and I'm going to look at its how it correlates with itself after a certain lag of time. So here's the sequence with the lag, and I'm not going, and I think you can make it quite clear that this product, the correlation of the product of these two, it's not going to matter. By the symmetry and the independence of the bits, it's pretty obvious that the autocorrelation is not going to be a function of absolute position in time, but only the relative lag between these two, because everything is equally distributed, everything is independent, it just doesn't matter. So for sure I've got this situation where it's R of tau, but now I want to calculate what is this autocorrelation function. So there's going to be two cases that I have to examine, and that depends on how large this lag is vis-a-vis the time of a bit. So we'll call capital T the time of a bit, and here we'll call this bit 0, bit 1, bit 2, and then there is some lag between this and itself, where we see the B0, B1, and B2 again. And in this first case, I'm going to assume that that lag is actually longer than the time of a bit. Okay, so I have something that's longer, that's why we see this. Tau is bigger than the capital T. And what does that mean? Well, now I'm going to calculate the expected value at all times, all time instants. And every time instant, when I do my averaging, my expectation operator, I'm going to be looking at a product of two bits which are different. Okay, it's not B0 multiplied by B0. It's always B0 by B1, B1 by B2, because this lag is bigger than the time of a bit. But I know that these B0s and B1s are independent. I assume that they're random, they're plus or minus 1, which means the expected value of the product is 0. Okay, so equal probability of plus or minus 1, the probability of the product is 0. So that means that as long as tau is greater than 0, as long as tau is greater than capital T, that the expectation will give me 0. Okay, that's good. Now let's go to case 2. Well, what happens when tau is actually less than T? So in this example, here's tau, and it's smaller than the time of a bit. Well, in this case, when I'm looking at the product and calculating the expectation, there will be a certain part of the time when the data is the same. Okay, so I have a B0 on top, I have a B0 on the bottom, and when I multiply those two together, I don't get an average 0, because when I multiply 1 with a 1, I get a 1, and when I have a minus 1 and multiply by minus 1, I get a 1, and so it's not averaging to 0. In this case, the larger that tau is, the smaller that the autocorrelation is. So as tau, gets closer and closer to a full bit, then this overlapping part, when I have the same bit multiplying it, becomes smaller and smaller. So the greater tau, the smaller the autocorrelation. And I think that that argument is probably enough for you to see that the result of this calculation of the autocorrelation function would be a triangular function. That I start here at the maximum, and that it goes off linearly, and that once the overlap is, that the lag is greater than the time of a bit, it goes to 0. And so this is the equation for the autocorrelation function for this sequence of rectangularly shaped random bit sequence. And of course, if it's triangle in the autocorrelation function, I know that I can take the Fourier transform pair to find the power spectral density. And in the case of the triangle, when I look for this power spectral density, I'm going to get the sinc squared. And so this is the power spectral density. And this was the example that was used, if you recall, in calculating the bandwidth different definitions of bandwidth. And this is one reason why it's an interesting example to have examined. So the last random process that I want to discuss with you is what we call additive white Gaussian noise. Very important random process. So this is a random process. When I reach in the hat, I bring out a noise sample, and at each instant of time for additive white Gaussian noise, the way I describe this particular random process is at any instant of time, it is a Gaussian. So here is the Gaussian distribution, and this n, it could be any instant of time that I look at, it's going to have the same distribution. So they are identically distributed, and it's zero mean with a certain variance that's indicated. Now, on top of it, for additive white Gaussian noise, I make the assumption that these samples are independent. So the samples are not only uncorrelated, but they're completely independent. So if they're independent, then the expected value of n of t with any delay is, well, if the delay is 0, then I've got the process with itself. But if it's not 0, then they're completely independent. There's zero mean. Because there's zero mean and they're independent, it would just be 0 times 0. And so that gives me a functional dependency of tau, which is the Dirac delta function. So if tau is equal to 0, there is complete correlation. They're the same thing. But if tau is anything non-zero, it's completely 0. So definition of the delta function. So that tells me that for Gaussian variables with this independence, that means that if I want to get the joint density function of any pair, any samples at all, I'm going to just get the product. And this is by the independence. So it's just the product of the marginal distributions. And the marginal distributions, I said, it was always the same. It's always the zero mean Gaussian random variable. So that means if I have samples at any two instants of time, gives me noise sample 1 and noise sample 2, that the joint density function of these samples is just the product of this Gaussian, two Gaussian distribution densities. So what does that mean? That means that that means if I look at the autocorrelation function, it is the variance, and here I'm going to call the variance n0 over 2. That was my sigma squared. I'm going to give it another name here, another way of writing it. Is this delta function. And so I know that the Fourier pair gives me the power spectral density. And for a delta function, the Fourier transform is a constant. So that means that in the frequency domain, the power spectral density is just a constant. And we call this n0 to be the noise density, and the units are watts per hertz. And the reason that we call this additive white Gaussian noise is because all of the frequencies are present. This is a constant. The density is completely flat, which is white light contains all frequencies of light. And so that's the nomenclature where it comes from. So the important thing to realize is that the additive white Gaussian noise has a completely flat, constant power spectral density, and that is a direct consequence of having a delta function for the autocorrelation function. So if that is additive white Gaussian noise, what happens when I filter that noise? So we know that for a linear time invariant system, the power spectral density at the output is just the power spectral density at the input multiplied by the square module of the frequency response of the filter. For instance, a low pass filter or whatever filter we want to do. So the noise at the input we know is constant no matter what the frequency is. And if I assume for this example that I have a perfect ideal low pass filter, that means that at the output I would have something rectangular where I have the level of the noise, which happens in the pass band of the filter, 0 everywhere. And because this does not contain all of the frequencies, it is no longer white, and we call this colored noise. So this would be a derivative, if you will, of the additive white Gaussian noise. So colored noise, if it has a, for instance, in the case of this example for an ideal low-pass filter, that would mean that the autocorrelation function would be a sinc function. And so that means that there's no longer completely uncorrelated noise samples, and that in general there is some correlation between them. So if I want completely uncorrelated, it would have been that delta function, which I found for white noise, but colored noise is not the case. It does have finite power because I can, and this is a square integrable function, unlike here where it was white noise. If I try to look what was the total power of this signal, it would be infinite. So it's a good model, but not very physical. Here with colored noise, that problem is resolved. I will notice that there are points at which the autocorrelation function goes to 0, and that would mean that at those points, the samples would be uncorrelated and independent. And so I'm going to end this discussion finally, having finished discussing random processes, white and stationary, additive white Gaussian noise, with why was it called the noise equivalent bandwidth? And now we can sort of understand where this comes from. Noise equivalent bandwidth would be if we put some total amount of energy like it was filtered noise. So if I had a filtered noise by perfect low-pass filter, I would have this rectangle of the noise that was let through. And if I have some sort of arbitrary shape, and I looked at the area under the curve and these two were equal, it would be like if I passed a white noise through a rectangular filter, it would have given me the same amount of noise as if I had used this other filter with an arbitrary shape. Okay, so that covers this discussion of random processes and the description of additive white Gaussian noise.